Okay, and so exponential functions are really helpful for us to be able to model real-world data. It's not very helpful to just talk about kind of what the functions look like in math. It's helpful to see kind of how these are applied in the real world. So a couple of equations where these exponential functions are really helpful is in talking about growth and decay, whether that a lot of times that shows up in talking about money. So a couple of formulas that are helpful to know that relate to money and the way that interest works. And I'm going to use the letter T here for time, so that we use f of t, P for principal, and then our interest works by we have 1 plus r, which is our interest rate, raised to the t power. And so this is talking about using an annual interest rate, and then t represents time in years, r is talking about your interest rate, and p is your principal. We could also kind of add a version of this where you don't get interest every year, but maybe you get interest more often than that, and so we would throw in an n value, r over n, and n is talking about the number of times you're compounding interest every year. And so these two formulas really aren't all that different. You'll notice that the first formula is basically exactly the second formula, but with n equals 1. So it's just kind of a special case of the second formula. And so this is our compound interest formula. And we are compounding interest n times per year. And so we can use this to talk about how money grows in a savings account, or maybe how this is used to calculate formulas of how you might pay for that credit cards, or pay off a car loan, or pay off a mortgage. It gets a little bit more complicated, but they all come back to kind of using this formula as the main idea. Okay, so we can think about, what if you take $3,000 and you put it into a savings account where a savings account you might get about, I'm going to say 2% interest. It's actually probably pretty high for a savings account. That is compounded quarterly, so that would be 4 times a month. That would mean n is 4. It's actually fairly common for savings accounts to pay out interest quarterly, which would be once every 3 months. And so when we're using 2% interest, we're not going to use 2 in the formula, we're going to use 0.02. So keep in mind that this 2% here, we're going to express it as a decimal, as 0.02, and that's what we're going to use in the formula. So you might ask a question like, how much money will you have after, I don't know, let's say 4 years? How much money will you have after 4 years? And so you can plug in the amounts that you know. $3,000 is your principal. 2% would be your interest rate, that 0.02 would be your R value, and then 4 years would be your time t. And so we just plug those values into your formula, and because we're compounding quarterly, n would be 4. And so we would use f of t equals 3,000 times 1 plus 0.02, and we're compounding quarterly, so divided by 4, that's where that n value was in the formula, raised to the 4, so we're actually plugging that 4 in 2 different places, times t, and t is also 4. We're talking about how much money you're going to have after 4 years. And you can plug this into your calculator and figure out what you get as a decimal. Hopefully it's pretty clear that you're going to have just over 3,000. Yeah, so you can think about kind of being able to simplify this a little bit. This is going to be 1.005 raised to the 16 power, and think about being able to plug it in your calculator. You can either plug it in one step at a time into your calculator, be careful of order of operations, or you can plug it in all at once in your graphing calculator, and you can get one answer. And so you get an answer like $3,249.21 if you're rounding. And that doesn't seem like it's a ton of money, but remember, you're only getting 2% interest, so it's not a lot from your savings account. If you put your money into a stock market, you'll get 5, 6, 7%. You'll have a bit more money after 4 years. So we can talk about increasing in the amount of money. Unfortunately, sometimes you owe money, and so the amount of money you owe increases, but it kind of increases in the same way. And so we can use exponential functions to model growth, whether it's money or whether it's populations, whether it's bacteria growth. This is used a lot in biology and chemistry, all over the place in the sciences. And using exponential functions is probably the most applicable kind of function we can use to model real-world data.